Polynomial synthetic division, back to the good old days. We're talking about another way to divide polynomials, so let's get started. Just as a reminder for you, synthetic division, we can use this when we are dividing by something in the form of x minus k. So for example, I would not be able to divide this polynomial if this was like x squared minus 2, or x squared plus 2x minus 4, and so on. The only way I can do this is if it comes in the form of x minus k. So let's divide. As a reminder to you guys, whenever we do synthetic division, we are always going to use the value of k. So x minus k. K here is 2. Okay. I'm going to write the leading coefficients of all my terms for x. Now I have an x to the 4th. Its leading coefficient is 1. Notice that I'm missing an x cubed term. So I need a placeholder 0. -3. I'm missing the x term, so I need a placeholder 0 and 1. Boom. Okay. Next, I always drop the first number, and I get 1. 1 times 2. We always multiply this diagonal way. 1 times 2 is 2, and we add vertically. Multiply 2 times 2 is 4. Add vertically. 1 times 2 is 2. Add vertically. 2 times 2 is 4, and we add vertically. Now, of course, that needs to mean something, right? We can't just write our answer as 1, 2, 1, 2, 5. That makes no sense. So to figure out what our solution is to this, I always like to kind of block this off and remind myself that that's my remainder, and I'm going to build up constant x, x squared, x cubed. So solution, 1x cubed plus 2x squared plus 1x plus 2 plus remainder over divisor. Boom, shakalaka. Yeah. Now, I think I missed something. Okay, so now it said find f of 2. Okay, well, we actually have this really awesome theorem that we're going to look at down here. It's called the remainder theorem. This is something you guys probably want to write down. The remainder theorem says that if a polynomial is divided by x minus k, then the remainder is f of k. So what that means is if I wanted to find f of 2, I would just need to synthetically divide by 2, which we did. We already divided by 2. So the remainder theorem says that a function's value at a point is equal to its remainder. In that case, 5 was the remainder. Therefore, f of 2 equals 5. I could also verify that if you didn't believe me, you're like, what are you talking about? Remainder theorem, you're crazy. I mean, we could literally test it out, plug it in, right? Times 2 squared plus 1. If I do that, okay, I would get 5. So remainder theorem says that a function's value is equal to its remainder when we synthetically divide. Okay, so it says given that x plus 3 is a factor of f of x, find all the zeros. Now, if something's a factor, remember that it divides evenly into this polynomial. And if something divides evenly into a polynomial, what would its remainder be? Well, its remainder would be 0 because it divides evenly. So if I want to find the remaining factors, I'm going to synthetically divide, right? In this case, k is -3. I have 5, 18. I'm double checking that I don't have any placeholders here. Very good. Now, because we know that x plus 3 is a factor, what should this remainder be? Yeah, we just talked about it. It should be 0. Okay, why don't you guys go ahead, put me on pause, synthetically divide this bad boy, and see if you can factor the quotient. Go ahead. Okay, so I synthetically divided. I did get that the remainder was 0. When I build this back up, I got 5x squared plus 3x minus 2 set that equal to 0, and I factored it. Now, if you're having trouble figuring out how I went from this step here to its factors, there's a couple methods you could use here. One, you could just guess and check. Two, you could use split the middle term as a method here for sure. Remember, we multiply a times c and so on. If you need to review that, make sure you do that. But key thing here is being able to factor this, and I get that all of my roots are all my zeros, it asks for our zeros, are at x equals given -3, found 2/5, and -1. Very, very nice. So our factor theorem. Our factor theorem says that a polynomial f of x has a factor x minus k if and only if f of k equals 0. What does that mean? It means that if the remainder is 0, then it is a factor. Incredible stuff. Okay. Next example here, probably the coolest example. We're going to show that 2 minus root 5 is a solution to the equation and find the remaining solutions. Now, if x equals 2 minus root 5 is a solution, then we also know what else has to be a solution. You're right, 2 plus root 5. How do we know that? Once upon a time, we learned that radicals have to come in pairs, come in their conjugate pairs. And that makes sense. Think about how we would get 2 minus root 5 as an answer. At some point, we would have to take a positive, negative square root, plus or minus square root. So if negative root 5 to minus root 5 is a solution, so would its positive. That makes sense. So now that I know that those are two solutions, I actually can write those as factors. X minus 2 minus root 5, and actually let me write these side by side, and x minus 2 plus root 5. I'm writing this in the form of x minus k, x minus k. Let's go ahead, using the associative property, I'm actually going to reorganize this so that way the parentheses are grouping the x minus 2's. And we can do that. Again, that's that associative property. It's been a while since I've even thought of that word. Okay, that's kind of cool. Well, okay, I have x minus 2 here and here. I have a minus root 5 and a plus root 5. Hey, this is kind of like dots, but backwards. So if I were to multiply these out, I could literally FOIL out these terms, or I could just recognize that this is kind of the form of a minus b, a plus b, and I know if I multiply this out, that's just a squared minus b squared. That's what I was saying, the reverse of dots. So I'm just going to write this as x minus 2 squared minus root 5 squared. Okay. Well, if I multiply that out, I get x squared minus 4x plus 4, and root 5 squared is just 5. Okay. Not bad, not bad. So I know that x squared minus 4x minus 1, its factors are these two up here. Right? Follow it backwards. It has the two factors of 2 plus root 5, 2 minus root 5. So now, if I were to synthetically divide, if I were to long divide that by this guy, I should get my final solution, my remaining solution. Oops. Let's bring that down here. We're going to need some space. Okay? So what I would like you guys to do, call me crazy, but I would like you guys to divide x squared minus 4x minus 1 into this cubic. Go ahead and put me on pause. Okay, so I did my long division and notice that I got a remainder of 0. Does that make sense? Well, yeah. I divided it by a polynomial that I constructed from 2 of its zeros, 2 of its factors, really. And I got remaining was x plus 3, which does tell me my third and final solution. Here are my 3 solutions. X equals 2 plus root 5, x equals 2 minus root 5, and x equals, if I set this equal to 0, negative 3. All right, you guys, so in conclusion, long and synthetic division can be used to find zeros of polynomials, right? Long division, we divide by a term with the highest degree, multiply, subtract, and repeat. Synthetic division, the only divisor is x minus k. That's the only time we can do that. And we add terms vertically, very important, and we multiply by k diagonally.